Welcome to Sanjoy Nath's Geometrifying Trigonometry. First, you have to understand that we have placed the frequencies of the music notes at a very higher level precision. I should tell you the units taken here are an engineering unit where precision is taken a very high range. It is taken as the Armstrong unit so that we can get high precision values. We have taken the precision for the angles in the decimal degrees such that we can get the high precision values to calculate the tempo and the micro tempo. We are not taking it clockwise, we are taking it the anti-clockwise, because from the east side, that is the positive x-axis, again we are returning back after the 360 degree when the whole song is complete. As per the Sanjoy Nath's Geometrifying Trigonometry parser, we have taken that 11,000 microsecond duration to calibrate to the 360 degree. BPM is taken as 180 such that milliticks per note is taken as a 17 milliticks per note, and microseconds taken as a 960 microseconds to ticks per quarter note. Calculation on microsecond per minutick is 347.22. that is a very high resolution calculation, and so we are not taking very long song, but still we have taken 3700 notes. Here in this video we are trying to explain that our human ear cannot perceive every kind of instrument with the different kind of timbres at every kind of frequency. If we take it longer duration of notes, then it's okay that our human ear can listen it, but for the longer duration of the notes there is a problem that every kind of wave cannot carry on for long time. Some waves can carry on for short time only, like a greeted ting, which cannot continue for 3 seconds. We know there is a damping factors, but piano rings can for a long time. The clarinets can can end the 3 seconds or 6 seconds continuously. Shanai has the effects that it can continue because the blowhorn kind of things, and which can continue for a longer time because how much you are blowing it will continue to play. But for guitars, that is a ting sound will not continue for 3 seconds or 6 seconds if you put the duration of the notes up to that long time. Another problem here is that every kind of notes and every kind of frequency with every kind of instruments is not perceivable to human ears for very long time. So for very short time. For suppose if I don't give sufficient time for a clarinet and a shanai, suppose I am giving only 1/100th of a second, then you cannot identify the differences between the shanai is playing or a clarinet is playing, because the perceivable limit, the minimum limit for the human ears is different for different instruments, and different instruments have different timbres of the waveforms, and for every different kind of frequency the perceivable limit of human ear is also different. For dogs and for mosquitoes, this perceivable limit is much more sharper than human, so they can perceive more number of notes with different kind of instruments. They can say the differences between the clarinets and the shanai when they listen it for a very short time, say 1/100th of a second. But human cannot understand. Human ear cannot recognize every instruments at every frequency at a very short time of the durations. Here we are doing the experiments with different kind of notes of the lower frequency and also with the higher frequencies with the different kind of instruments, and we have used 108 number of instruments such that we can show you the differences between the note durations with which we can see and we can visualize with our ears, and we can visualize with the CAD geometry also with this kind of images that I am trying to show in the video, and where these images have everything are the line segments, and the line segments are generated with the hatch patterns or on the triangle geometry generated with the geometrifying trigonometry concepts, and with that all the line segments are interrelated with each other, and we have placed it with the concentric circles. Every circle has a frequency range, that is the radius of the circles are shown in the units of hertz. And if we change these units to the millimeter to the decimal, then we can see the radius values properly. So the precision is taken as the Armstrong, okay, that is taken as the Armstrong, but we have taken the units now to the millimeters such that we can show you the frequency ranges, that 164.81. Here For your clarity, we have kept the notes frequencies, and all kinds of note frequencies are not available for all kind of instruments. Suppose for 25.96 hertz, there is no instrument can play with that with the proper significance, because the timbres you cannot recognize with the ear. The octave starts with the A0, which has the 27.5 hertz. A0 sharp has a 29.14 hertz. B0 starts with the 30.87 hertz, and in this way every different instruments can play with these styles, and 13289.75 hertz is the maximum limit of every instruments with which we can play. We cannot assign more than these frequencies for the MIDI notes, because MIDI don't support more than this frequency. 13289.75 is the highest frequency. This hertz is the highest frequency for the musical notes. And we can see that there is another note that I have kept here for your demonstration, that different kind of instruments. We have 128 instruments, and but out of that I have not kept the 20 instruments here, because those instruments are not for the melody instruments. Those are for the percussion instruments. I try to avoid the percussion instruments, and these are kind of the waves like the square wave, sawtooth wave, Calliope, Clifford waves, Sharang wave, the voice solo, and these kind of waves, and I have not kept in our music generation systems, because for those things I will do the separate kind of programming, so that we can show the waveforms. Timbres have the different frequency ranges for our human ears recognition systems. The different kind of notes that we can play with these changes with the instruments that we are choosing. From the instrument number 35, suppose the instrument number 35, the electric bass 276, these are the percussion instruments. And percussion instruments has a specialty that we as a human can have very short time duration to recognize the percussion instrument. Suppose human ear can recognize in the 1/20th of a second if a percussion instrument is played, and the duration to which the percussion instruments can damp out is also very small. So we cannot put very longer note duration for the percussion instruments. We can put very short duration instrumentation with the percussion instrument, but for the melody instrument we can play it with 1/10th of a second to 6 second. It's good to listen. If we put a melody instrument for more than 10 seconds, then it will listen very odd. These are the music theory part, but we are not talking about the music theory. We are trying to make the geometry interpreted as a music, or music interpreted as a geometry. We are trying to do those things, and mainly we are trying to do it with the triangle geometry and line segment geometry, because geometrifying trigonometry is having with the triangles and line segments only. And the motive of Sanjoy Nath's geometrifying trigonometry is to convert every trigonometry expressions to triangulations, and every triangulations exploded into the line segments, and every line segments are interpreted as the musical notes. Then the next phase comes, the how long the note is, how many microseconds the note is playing. On those conditions we assign the instrument such that it can have a rhythmic behavior and also the melodic behavior. Let's listen how it looks in our ear and how it looks in our eye. The geometry is shown and also the music is shown parallelly on the screen. We are explaining the things here. We are showing that every line segments are exploded, which are the hatch patterns on the triangles, and the triangles are generated with the geometrifying trigonometry algorithms used on the trigonometry expressions. Then these kind of patterns are forming, and these patterns have a musical interpretation, and every music has a pattern interpretation on the CAD geometry if we take it the high precision values. Let's listen how it looks like in our ear and how it looks like in our eyes. Let's see. It is not AI generated music, it is entirely calibrated, calculated music generated from the geometrifying trigonometry. Geometrifying trigonometry generates the line segments, and line segments are interpreted as the notes for music theory, and it is interpreted as the music. And the MIDI file is generated from the CAD geometry, that is generated from the trigonometry expressions through the geometrifying trigonometry protocols. It is not AI generated music, it is entirely a theory dependent music generation in the rule based geometry and the geometry to music. Thank you.